In our everyday world, barriers feel absolute. A wall blocks your path. A mountain resists your climb. A locked door stands firm until you find the key. We live with the sense that matter is solid, that obstacles are impenetrable, that you cannot be on one side of a wall and suddenly appear on the other without passing through. Yet in the hidden domain of the quantum, reality is not bound by such ordinary rules. In that realm, the impossible happens not once in a while, but constantly. It happens so often that without it, the stars would not shine, the ground beneath your feet would not radiate warmth, and even your own body would not persist. This strange rebellion against common sense is called quantum tunneling. To imagine it, picture a ball rolling toward a hill. The ball has only a little speed, not nearly enough to climb the slope and reach the top. Classical physics, the physics of Newton, tells us what happens next. The ball rolls up part of the slope, slows, stops, and then rolls back down. Energy is conserved, cause and effect are preserved, and no miracle occurs. The ball does not suddenly vanish and reappear on the far side of the hill. But a particle in the quantum world does not behave like that ball. Its essence is not a tiny dot of matter marching along a line. Instead, it is described as a wave of possibility that spreads across space. When such a wave collides with a barrier, part of it reflects, part of it lingers, and part of it seeps through, even if by every classical rule, it should never cross. The particle is not guaranteed to appear beyond the hill, but there is a chance, a measurable probability, that it will be found there. This is the essence of tunneling. It is not magic in the sense of breaking physics, but it is magic in the sense of breaking our intuition. Imagine trying to walk through a locked door and finding that if you tried enough times, there would be a faint chance of suddenly standing in the next room without ever turning the knob. You might say that chance is so tiny that for human-sized objects it is effectively zero, and you would be right. Yet for electrons, protons, neutrons, and the whole family of subatomic particles, tunneling is not just possible, but inevitable. What makes tunneling so haunting is that it reminds us that the world is not built from hard marbles clattering in the dark. It is built from delicate waves that obey equations stranger than dreams. One such equation, formulated by Erwin Schrödinger in the 1920s, describes how these waves evolve and what they mean. When you solve it for a particle near a barrier, the mathematics predicts that the wave never drops perfectly to zero at the wall. Instead, it fades exponentially, as if the barrier were swallowing it. And though most of that wave dies inside, a sliver always makes it out the far side. That sliver is what makes tunneling possible. Tunneling matters because the universe is filled with barriers. Protons repel each other with fierce electric force. Electrons are held in atoms by potential walls. Nuclei trap their constituents in wells of immense energy. If those walls were perfectly solid, almost nothing could happen. Fusion would stall, radioactivity would halt, chemistry itself might be crippled. But because of tunneling, the impossible becomes the ordinary. This phenomenon shakes our sense of reality. Classical physics taught us that the universe is a clockwork, each gear turning predictably, each cause leading to a clear effect. Tunneling shows that nature runs on a different script, one written in probabilities, not certainties. The barrier does not forbid, it only discourages. The wall does not block absolutely, it only resists. And the more one learns about tunneling, the more one realizes it is not a footnote of physics, but a central theme. So the story of tunneling begins with an image that should be impossible, a ball that has too little energy to climb a hill, yet somehow, by the rules of the quantum, finds itself on the far side. To make sense of this, to move beyond the metaphor, we must embrace the idea that particles are not dots, but waves. Only by stepping into that world of overlapping ripples and mathematical symphonies can we understand why tunneling works at all. And so, to grasp the impossible made possible, we must next learn why matter behaves like a wave. The leap from particle to wave is not natural to the human mind. Our senses tell us that matter is solid, that it occupies a single place, that it can be grasped, touched, weighed. For centuries, this view went unchallenged. But at the dawn of the 20th century, light itself forced us to reconsider. Experiments showed that light could act like a wave, spreading in ripples, bending around corners, interfering like overlapping rings in a pond. Yet other experiments revealed light behaving like a particle, arriving as tiny quanta, later called photons. The world of physics was shaken. If light could be both wave and particle, what else might share this dual identity? The answer came in 1924, when Louis de Broglie, a French physicist, proposed something radical. He suggested that all matter, not just light, possesses a wave nature. An electron, so familiar as a particle, also behaves as a wave with a wavelength determined by its momentum. Soon afterward, experiments confirmed his prediction. Electrons fired at a crystal formed interference patterns, just like light passing through slits. These patterns could not exist if electrons were only little dots. They existed because electrons, like light, were also waves. This revelation was not a curiosity. It was the foundation of quantum mechanics. If particles can be waves, they can spread. If they can spread, they can overlap barriers. If they can overlap barriers, they can tunnel. The path to the impossible was opened not by magic, but by mathematics. Schrödinger gave this new idea its mathematical language. His equation, written in the 1920s, describes how a wave of probability evolves over time. Unlike the familiar equations of Newton, which tell you exactly where a planet will be at every future moment, Schrödinger's equation offers only likelihoods. It does not say an electron will be here. It says there is a 70% chance of it being here, a 20% chance of it being there, and a 10% chance of it being somewhere else. When a barrier appears, the equation does not allow the probability wave to stop dead. Instead, it allows part of it to seep through, fading as it moves, but never vanishing entirely until it emerges beyond the wall. This seeping is not like a ghost sneaking through. It is not a slow crawl. The mathematics shows that tunneling is instantaneous. The particle is not dragged through the wall, it is found beyond it. That defies classical motion, but it does not defy the mathematics of the wave function. And every experiment built to test it confirms the prediction. To feel the strangeness, imagine again the locked door. Each time you walk into it, you expect nothing but resistance. In the classical world, that is the only outcome. But if you were as small as an electron, your probability wave would not end at the door. It would thin, like a shadow pressed against the wood. Most of it would remain trapped, reflecting back. Yet a trace would leak through, spreading faintly into the room beyond. That trace is the possibility that when measured, you are discovered not in the hallway, but inside the locked room. It is not guaranteed, but it is real. This is not a rare trick. It is woven into the fabric of the cosmos. The sun itself would be dark without tunneling. Its core is not hot enough, by classical reckoning, for protons to overcome their mutual repulsion and fuse. Yet fusion happens constantly because tunneling lets them pass through the electric barrier. In radioactive elements, tunneling allows particles to escape the prison of the nucleus, producing decay. In modern technology, tunneling allows microscopes to see atoms and diodes to function. Everywhere you look, tunneling is there. But before we chase these wonders, we must linger on the essence. What does it mean that the wave leaks? The mathematics shows that inside a barrier, the wave does not oscillate, as it does in free space. Instead, it decays exponentially, shrinking rapidly with distance. If the barrier is thick, the wave nearly dies before reaching the far side, and the chance of tunneling is tiny. If the barrier is thin, more of the wave survives, and the chance is greater. This balance between thickness, height, and energy decides whether tunneling is common or rare. For human-scale objects, the barriers are enormous compared to the wavelength of matter, which is unimaginably small. That is why you cannot walk through walls. The probability is so minuscule that even if you tried every second for the age of the universe, the odds would still be effectively zero. But for particles, the scale is different. Their wavelengths are long enough, the barriers thin enough, and the time spans short enough that tunneling becomes inevitable. The lesson is both humbling and inspiring. Nature does not close doors completely. It leaves them ajar, just enough for chance to slip through. The universe is not made of certainties but of possibilities, and tunneling is one of the most direct ways we encounter this truth. And yet, this story is incomplete. To grasp tunneling deeply, we must understand the wave more fully. What exactly is leaking? How can a particle, which we detect as a single spot, be smeared into a wave that oozes through barriers? To answer, we must dive deeper into the mathematics of waves, probabilities, and decay. This path will lead us not only to the mechanism of tunneling, but to its role in shaping stars, elements, and life itself. And so, the mystery carries us forward. To appreciate how deep this idea goes, pause for a moment and imagine you are no longer a person walking through halls and streets, but a wave stretched across space. Your identity is not a single point, but a pattern, a rhythm, a set of peaks and troughs that describe where you might be found. You move forward, and suddenly, a barrier rises before you. In the old world of Newton, that barrier is absolute. You strike it and bounce back, but in the quantum world, part of your rhythm seeps inside, like a muffled song playing through a wall. Most of the music dies away in the thickness, but not all. A faint echo survives and emerges on the other side. When someone listens there, they may discover that you have arrived, though you never scaled the wall. This image is not fantasy, it is the actual language of modern physics. Experiments with electrons and semiconductors, with protons in accelerators, and with neutrons in nuclear reactions, all confirm it. What once seemed absurd has become routine in laboratories. Engineers even harness the effect deliberately, building devices that depend on tunneling to function. Far from being a marginal curiosity, it has become one of the cornerstones of science and technology, and yet, it carries a haunting lesson. If barriers are never truly absolute, then certainty itself is an illusion. What we call impossible may only mean highly improbable. The universe is not a fortress of rigid walls, but a landscape of possibilities, each path faint or strong depending on the wave that feeds it. This is why tunneling feels so cinematic. It is not merely a calculation, but a story, a drama of chance, slipping through cracks in reality. There is another twist. Tunneling does not take time in the way we expect. When a particle appears on the far side of a barrier, it does not creep through slowly. It does not dig a passage. Instead, it simply shows up, as if the barrier itself were less a wall than a veil. Physicists have debated how to describe this strangeness. Some measure the delay of the wave, others argue about definitions of traversal time. But the common agreement is that tunneling cannot be forced into classical terms. It must be accepted as a quantum event, one that sidesteps the ordinary rules of motion. Think again of the ball and the hill. No matter how often you roll the ball in the classical world, it will never cross without the energy to climb. But in the quantum world, each attempt carries a chance. The ball is not only rolling, it is also rippling, and ripples can sneak through in ways solid matter cannot. Over billions of attempts, the improbable becomes inevitable. The sun itself proves this, for without tunneling, its core could not fuse hydrogen into helium. The stars would freeze in darkness, and life would never rise. So tunneling is not a fringe act of defiance. It is a law, a mechanism, a constant whisper of possibility. It is one of those rare truths where the universe reveals its hidden generosity. The barriers remain, the walls still stand, but they are not perfect. They admit chance, they allow the improbable, they let the impossible slip through. And this is why tunneling matters to us. It is not only a rule for electrons and protons, it is a reminder that reality itself is built on uncertainty, that chance is not an afterthought, but a foundation. When we gaze at the stars, when we measure radioactive decay, when we switch on a device built from quantum circuits, we are witnessing the outcome of countless tunneling events. The impossible made possible is not a trick of imagination. It is the heartbeat of the quantum world. And to follow it further, we must embrace the wave itself. For if tunneling is the consequence, the wave is the cause. The next step in our journey is to explore how particles become waves, how those waves obey Schrödinger's equation, and how they leak into places they should never reach. Only then will the impossible truly make sense. To see why tunneling is possible, we must set aside the picture of particles as tiny billiard balls bouncing through space. Instead, we must accept that particles live double lives. They are both solid and not solid, both point-like and spread out, both present and uncertain. This duality is not a poetic metaphor. It is a measurable fact, revealed in experiments that change the course of science forever. The story begins with light. For centuries, scholars debated its nature. Isaac Newton believed light was a stream of particles. Christian Huygens believed it was a wave. Both were partly right, and both were incomplete. In the 19th century, experiments with interference and diffraction proved beyond doubt that light behaved as a wave, bending and rippling in patterns no particle could explain. Yet in the early 20th century, Einstein revealed that light also arrives in packets, discrete quanta of energy, later called photons. The revelation was stunning. Light was not one thing or the other, but both, depending on how you looked. If light could live such a double existence, perhaps matter could too. Louis de Broglie, a young physicist with a daring imagination, suggested exactly that in 1924. His proposal was audacious. He claimed that every particle has a wavelength linked to its momentum, and therefore must be treated not only as a mass of matter, but also as a ripple in space. It was an idea many dismissed at first, yet experiments soon vindicated him. Electrons fired at a crystal produced interference patterns, just like waves of light. The evidence was clear. Matter had a hidden wave nature. This changed everything. It meant that an electron orbiting an atom is not a tiny planet circling a sun-like nucleus. It is a cloud of probability, a standing wave that resonates in allowed patterns, much like the harmonics of a vibrating string. Each orbit corresponds not to a fixed path, but to a wave that fits around the nucleus. The very structure of atoms, the shapes of the periodic table, the rules of chemistry, all arise from this wave nature. But these are not waves of water or sound. They are probability waves, mathematical descriptions of where a particle is likely to be found. They do not tell us with certainty. They whisper in chances. A particle described by a wave function might be discovered here with high probability, there with some probability, or in a far place with faint probability. That faint probability is not nothing. It is the seed of tunneling. Schrödinger's equation gives these waves their form. It is the quantum law of motion, just as Newton's equations are the classical laws of motion. Feed in the potential energy landscape around a particle, and Schrödinger's equation produces the wave function. Place a barrier in its path, and the wave does not halt sharply at the edge. Instead, it seeps inward, decaying with distance, but never instantly vanishing. The mathematics does not allow a clean stop. It only allows a fade. This is why particles can tunnel. They are not bound to dots and lines. They are spread into waves that extend into forbidden regions. If the wave extends far enough beyond a barrier, then when measured, the particle has a chance of appearing there. The larger the wave's tail beyond the wall, the higher the chance. The smaller the tail, the lower the chance. But never is the chance zero. Think of it this way. A particle's wave function is like a shadow cast through glass. The shadow dims as it passes through, weaker and weaker, but it never ceases completely. On the far side, there is still a trace, faint but real, and that trace means the particle may be discovered there. This blending of particle and wave is the foundation of tunneling. Without it, barriers would be absolute. With it, the universe is full of doorways that are not fully locked. It is the overlap of waves with barriers that allows the improbable crossings to occur. And so the lesson is clear. To understand tunneling, we must understand waves. Particles are not marbles. They are symphonies, resonating in space and time. When those symphonies meet walls, they do not fall silent. They leak, they linger, they stretch beyond the forbidden. This leakage is not metaphorical. It is the very mechanism of tunneling, the reason stars burn and atoms decay and modern devices function. The next step in our journey is to explore this leakage more closely. How exactly does the wave decay inside a barrier? How does the thickness and height of that barrier shape the odds? And why does tunneling happen instantaneously, with no crawl or passage, but simply as an appearance on the other side? These questions guide us forward, deeper into the heart of the quantum world. The wave nature of matter challenges everything we thought we knew about how reality works. Imagine an electron approaching a wall. If we cling to the particle picture, the answer is simple. The electron collides with the wall and bounces back. End of story. But the wave picture complicates this certainty. The electron is described not as a point, but as a spread of probability, a rhythm across space. When that rhythm meets the wall, it does not end cleanly. It diminishes, thinning, fading, but continuing. The mathematics demands this, and the experiments confirm it. This fading is described as exponential decay. Each step deeper into the barrier reduces the strength of the wave by a constant fraction, so that the further it goes, the weaker it becomes. If the barrier is thick, the wave decays almost completely before reaching the far side. If the barrier is thin, some of the wave survives the journey. What matters is not whether the wave continues, but how much of it is left when it emerges. That remnant is what gives tunneling its chance. To bring this into a human picture, imagine your voice echoing into a heavy wall. If you press your lips against a thick slab of stone and shout, nearly all the sound is swallowed. Yet if the wall is thinner, or if the material is less dense, a faint murmur might be heard on the far side. Your words did not walk through the stone. They faded, diminished, and then carried faintly beyond. In the quantum world, The same is true for particles. They are not walking through walls, they are probabilities leaking through them. What makes this even more strange is that the leakage is not slow. A particle does not inch its way through, like water seeping across cracks. Instead, the mathematics shows that tunneling is instantaneous. When the particle is detected on the far side, it is simply there, with no trace of a path in between. This is one of the most unsettling aspects of tunneling, for it resists every classical analogy we try to force upon it. Time itself feels different in the quantum world. Schrödinger's equation paints this clearly. When you solve it for a particle facing a barrier, the solution inside is not an oscillating wave like the free regions outside. It is a decaying exponential, dropping in strength step by step. The greater the barrier's height, the faster the decay. The greater the barrier's thickness, the more likely the wave will vanish before reaching the far side. But never does it vanish instantly. Always there remains a tail, however faint. That tail is the seed of tunneling. Even more surprising, the leakage is not restricted to simple barriers. Nature is full of complicated potentials, landscapes of energy, with valleys and peaks. In every case, the mathematics predicts that if there is a barrier, there is always some probability of a particle appearing beyond it. The scale of that probability depends on the wave's energy, the shape of the barrier, and the distance to be crossed. But the principle is universal. The universe allows no absolute walls. Physicists have tested this principle countless times. They build devices where electrons face insulating layers and watch as current flows anyway, carried by tunneling. They measure radioactive elements and find their decay rates match the predictions of tunneling probabilities. They shine light on tiny junctions and see electrons leap across gaps that should be impassable. Each experiment reinforces the same truth: the wave leaks, and tunneling follows. It is here that the wave picture of particles becomes unavoidable. If you cling to the idea that a particle is a dot, tunneling is impossible. But if you accept that the particle is a wave of probability, spreading across space, then tunneling is inevitable. The wave does not respect the rigid borders of classical matter. It stretches, overlaps, and fades, but never halts. This understanding reshapes how we view the universe. Atoms are not shells of hard marbles, orbiting one another. They are symphonies of waves, bound and resonating in patterns described by probability. Chemistry is not a game of balls clattering together, but of waves overlapping, interfering, and blending. Physics itself is not a script of certainties, but a dance of chances. Tunneling emerges from this dance as one of its most dramatic steps. The walls that appear solid in our imagination are not truly solid. They are merely steep hills in the landscape of probability. Particles, as waves, always have a chance of flowing beyond. The chance may be tiny, but it is never zero. And given enough time, even the tiniest chance becomes reality. This is why tunneling is not an exception to the rule, but part of the rule itself. It reveals that the universe does not work like a machine built from gears and rods. It works like a score written in probabilities, each note vibrating through barriers, each chance waiting to be realized. And so we arrive at the heart of the mystery. The leakage of the wave function is not an accident. It is the essence of the quantum world. It explains how particles escape nuclei, how electrons flow in circuits, how stars ignite. It is the bridge between the impossible and the inevitable. But before we turn to those grand consequences, let us first examine the mechanics of tunneling itself. How does a wave behave inside a barrier? How do physicists calculate the odds of crossing? And why is the process instantaneous, as if the particles skipped the journey entirely? The answers lead us directly into the workings of tunneling, and they will show us just how strange and yet how precise this phenomenon truly island. The mathematics of tunneling is both elegant and unforgiving. When a particle approaches a barrier, we describe it with a wave function, a mathematical form that carries all the probabilities of where it might be found. Outside the barrier, that wave oscillates like a familiar ripple, rising and falling in rhythm with the particle's momentum. At the edge of the barrier, however, the wave changes character. It no longer oscillates but decays, shrinking rapidly with distance. This exponential decay is the key. It means the barrier is not a perfect wall but a filter, allowing only the faintest trace of the wave to pass through. If the barrier is very tall compared to the particle's energy, the decay is severe, and the chance of tunneling is nearly negligible. If the barrier is modest or thin, the decay is weaker, and the wave has a greater chance of surviving to the other side. The mathematics provides exact formulas for these probabilities, and they match experiments with remarkable precision. Every time physicists measure the rate of radioactive decay, or the current through a thin insulating layer, they find the numbers agree with the predictions of wave function leakage. This precision makes tunneling one of the strongest confirmations of quantum mechanics. It shows that the theory is not just a philosophical speculation, but a practical description of reality. The equations do not merely suggest that particles might tunnel, they calculate how often they will, how likely it is, and under what conditions. The fact that nature obeys these predictions is what gives scientists confidence that the wave description of matter is real, however strange it may seem. One of the most unsettling aspects of tunneling is its apparent disregard for time. In the classical world, crossing a distance requires duration. A ball rolling across a floor takes measurable seconds. But in the quantum world, tunneling defies this intuition. When a particle appears on the far side of a barrier, it does so without a detectable journey. The wave function inside the barrier does not correspond to motion as we understand it. It corresponds only to probability decay. Thus, when the particle is found beyond the barrier, it is simply there. Some experiments have tried to measure the time it takes, and debates continue about definitions, but the consensus is clear. Tunneling cannot be understood as a particle moving through space in the classical sense. It must be accepted as a phenomenon of probability itself. This idea forces us to rethink what it means for something to be real. If a particle does not take a path, but instead has a chance of appearing beyond a barrier, then reality is not about definite locations and motions. It is about possibilities, about where the particle might be found when observed. Until measurement, it is not locked into a single fate. It is spread across options, each weighted by its wave function. Tunneling is the manifestation of that spread. To bring this home, picture again the ball and the hill. Classically, the ball must climb, and if it lacks the energy, it fails. Quantum mechanically, the ball is not just a point, it is a wave. That wave extends into the hill, fading as it climbs, but always carrying a sliver beyond. If that sliver survives, then there is a chance the ball will be discovered on the far side. The larger the sliver, the greater the chance. Over countless trials, some of the balls will appear where they should not, proving that the impossible has become inevitable. This inevitability reshapes our picture of the universe. Stars shine because tunneling allows fusion at temperatures that would otherwise be too low. Nuclei decay because tunneling lets particles escape. Atoms exist as they do because electron waves overlap and leak in ways that shape chemical bonds. Even modern technology, from diodes to microscopes, relies on tunneling. It is not a rare curiosity, but a universal principle. And yet, there is still a sense of mystery. Why should the universe permit such leakage? Why should probability waves exist at all? These are questions that touch the boundary between physics and philosophy. For now, the mathematics gives us answers precise enough to build devices and predict lifetimes of radioactive isotopes. But the deeper meaning, the reason why reality is probabilistic, remains one of the great puzzles of science. What we know is this: the leakage of the wave function is the essence of tunneling. It is why barriers are never absolute, why the universe is not a cage of certainties, but a sea of chances. To understand tunneling fully, we must accept that particles are not dots but waves of probability, spreading, fading, and sometimes appearing where they have no right to be. This realization prepares us for the next step. Having seen how waves decay inside barriers, we can now explore the details of how tunneling works in practice. How do physicists calculate the odds? How do thickness, energy, and height combine to set the probabilities? And how can we visualize the process when it seems to happen without motion at all? These questions lead us into the mechanics of tunneling itself, where mathematics and mystery intertwine. When we imagine a particle tunneling through a barrier, the temptation is to think of it as squeezing or drilling, like water soaking through a sponge or a worm boring through wood. But tunneling is not like this. The mathematics tells us that the particle does not move through the barrier in any classical sense. Instead, its probability wave enters the forbidden region, fades exponentially, and if the barrier is not too thick, emerges on the far side. When measured, the particle is simply there, as if the wall were never a perfect blockade, but a translucent veil. This is the power of Schrödinger's equation. It shows that the wave function outside the barrier oscillates, corresponding to motion. Inside, however, the solution is no longer oscillatory. It is exponential decay. The thicker or taller the barrier, the sharper the decay, and the smaller the chance of finding the particle beyond. But crucially, the the chance is never zero. Even with barriers vastly higher than the particle's energy, the mathematics insists on a finite probability. The wall is firm, but never absolute. To give this idea flesh, imagine a traveler in a desert approaching a mountain ridge. Classical physics says that unless the traveler has the strength to climb the ridge, they cannot reach the valley beyond. Quantum mechanics says that even if the traveler has no strength to climb, there is still a faint chance they will be discovered in the valley, without ever having scaled the peak. The mathematics of the wave function ensures that some possibility always spills beyond the ridge, however small. What matters most are three factors. First, the width of the barrier. A thicker wall allows less of the wave to survive. Second, the height of the barrier compared to the particle's energy. A higher wall kills the wave more quickly. Third, the energy of the particle itself. A more energetic particle carries a longer decaying tail inside the barrier, increasing the odds of survival. Together, these elements determine the tunneling probability. Physicists can calculate these probabilities with remarkable precision. The formula shows that the probability falls exponentially with barrier width and height. Double the thickness, and the odds may drop not by half, but by orders of magnitude. Raise the barrier slightly, and the chance may collapse dramatically. This exponential sensitivity explains why tunneling is rare in the macroscopic world, but common in the microscopic one. For a person trying to walk through a wall, the odds are so unimaginably small that they might as well be zero. But for electrons facing thin atomic barriers, the odds are high enough to shape the chemistry of life. One of the most puzzling aspects of tunneling is its relationship with time. When a particle appears on the far side, it does not take the time one would expect from crossing a distance. Some experiments suggest that the effective tunneling time does not increase significantly even as the barrier becomes thicker. This has led to debates about whether tunneling occurs faster than light, but most physicists agree the question is framed incorrectly. Tunneling is not a journey with a speed. It is a probabilistic phenomenon, one that sidesteps the idea of traversal altogether. The particle is not moving through space, it is manifesting where its wave function allows. This makes tunneling feel more like a disappearance and reappearance than a passage. The mathematics agrees. Inside the barrier, the wave function is not oscillating like a traveling wave. It is dying like an echo in a cavern. When the echo is faint but survives long enough to reach the far side, there is a chance of discovery there. No motion, no path, just probability extended across forbidden ground. This understanding reframes how we think of barriers themselves. They are not impassable fortresses, but steep slopes in the energy landscape. A particle with insufficient energy cannot roll over the slope, but its wave extends into the hillside nonetheless. That extension allows a chance of being found on the far side. What looks like solidity is in fact porous, at least to the language of probability. For the universe, this porosity is everything. Without it, stars would not burn, elements would not form, and life would not arise. Barriers would hold too tightly, and processes essential to existence would halt. But because of tunneling, nature allows what classical physics forbids. The impossible is woven into the fabric of reality. And so, tunneling is not just a curiosity of mathematics. It is a mechanism with consequences on every scale. To see those consequences, we will leave the abstract barriers of equations and turn to the heart of the cosmos itself. The greatest furnace in our sky, the sun, shines not because of classical collisions, but because of tunneling. Without it, the stars would be cold and the universe would be dark. The heart of tunneling lies in the way waves behave when confronted with boundaries. In the classical world, a boundary is absolute. A ball rolls until it collides with a wall, and then it stops. In the quantum world, the wave that represents a particle can never stop so cleanly. Instead, it diminishes gradually, like a lantern's glow seeping through fog. The equations reveal this with merciless precision. Outside the barrier, the wave oscillates with a rhythm tied to the particle's energy. Each crest and trough marks the dance of possibility across space. But as soon as the wave enters the barrier, the rhythm dies. The oscillations cease, replaced by a steady decline. With every small step deeper into the forbidden region, the wave shrinks by the same fraction, an exponential decay that makes survival on the far side unlikely, but never impossible. This exponential nature is what makes tunneling so striking. In ordinary declines, like a ball losing speed to friction, the change slows over time until motion stops. In exponential decay, the loss is relentless. The wave is reduced by half, then by half again, then by half again, continuing without pause. Each extra bit of barrier consumes a proportional chunk of the wave, carving away at its strength until only the faintest whisper remains. Yet no matter how far the decay proceeds, there is always some remnant. This is why thickness matters so much. A thin barrier allows enough of the wave to survive that tunneling becomes frequent. A thicker barrier makes the odds collapse. Height matters as well. A taller barrier forces the wave to decay more quickly, killing most of it before it can reach the far side. This sensitivity explains why tunneling dominates the microscopic world, but is absent in the macroscopic. Human-sized barriers are vast compared to the wavelengths of matter at our scale. The wave dies long before it could ever emerge. Electrons, however, with their tiny mass and correspondingly long wavelengths, tunnel often. Consider a thought experiment. Imagine two mountains facing each other, with a deep valley between them. A traveler has too little energy to climb either mountain. Classical physics says the traveler is trapped forever in the valley. Quantum mechanics says otherwise. The traveler is also a wave, and that wave leaks into the rock of the mountains. Most of it fades away, but a faint remnant crosses the peak and emerges on the far side. Now there is a chance that the traveler will be discovered in the next valley, even though no climb occurred. The higher or wider the mountain, the smaller the chance, but never does the chance fall to zero. This idea is more than fantasy. Physicists have tested it with precision. In one famous experiment, they trapped electrons between barriers so that escape could only occur through tunneling. By adjusting the width of the barriers, they watched the tunneling rate fall, exactly as predicted by exponential decay. Each tiny increase in thickness caused the odds to drop dramatically, confirming the mathematics to extraordinary accuracy. What is most unsettling is that when the electron was discovered beyond the barrier, it left no evidence of motion through it, no trace, no path, no measurable journey. It was simply there, as if the barrier had been transparent to possibility, but opaque to motion. Some researchers tried to measure how long the crossing took, and the results were confounding. It seemed that tunneling did not scale with distance in the way travel should. Instead, the apparent time to tunnel through thicker barriers did not increase as expected, hinting at a process outside ordinary notions of speed. This has led to endless debates about whether tunneling is instantaneous or whether time itself behaves differently inside the barrier. But most physicists agree on one point. Tunneling is not motion in the classical sense. It is not a particle traversing space step by step. It is the manifestation of probability across a forbidden region. To ask how long it takes is to misunderstand the process. The better question is how often it happens, and that answer comes from the mathematics of exponential decay. This makes tunneling both strange and deeply practical. It is strange because it undermines our everyday notions of paths and journeys. It is practical because the mathematics allows precise predictions. By calculating the decay rate, physicists can estimate how often tunneling will occur. This is how they predict the lifetimes of radioactive isotopes, how they design devices that rely on tunneling currents, and how they understand the fusion reactions inside stars. And so, tunneling becomes not just a quirk of probability, but a tool, a mechanism that can be measured, tested, and used. The impossible becomes predictable. The forbidden becomes routine. Yet even as we harness it, tunneling retains its mystery. It defies the classical mind, refusing to fit into notions of motion and certainty. It reminds us that the universe is not a clockwork, but a sea of waves, and that in such a sea, barriers are never absolute. This understanding prepares us for the next leap. If tunneling is more than theory, it must be written into the engines of the cosmos. And indeed, it island, the greatest furnace of all, our sun, depends upon tunneling to shine. Without it, the protons at its core would repel each other endlessly, fusion would stall, and the universe would be dark. With it, light and life are possible. The journey from abstract mathematics to cosmic consequence awaits. The more closely we study tunneling, the more it reveals its dual nature. On one hand, it is a mathematical certainty that follows from Schrödinger's equation. On the other hand, it is a phenomenon that feels almost magical when described in plain language. A particle that lacks the energy to climb a wall can nonetheless appear on the other side. This duality between the strictness of the mathematics and the strangeness of the outcome is what makes tunneling so compelling. At its core, the mathematics tells us that the wave function cannot vanish abruptly. It must fade continuously, and that fading means there is always a tail. The thickness of the barrier decides how much of the tail survives. The height decides how steeply it dies away. The particle's own energy decides how long the tail stretches. From these three ingredients comes the tunneling probability. Though it may be tiny, it is always real. To grasp the importance of this, picture the universe if tunneling did not exist. Protons inside stars would repel each other too strongly to fuse, for even in the crushing heart of the sun, the temperature is not high enough to push them together by brute force. Without tunneling, the sun would never ignite, and the galaxies would remain dark clouds of hydrogen. Radioactive decay would not occur, and the heavy elements forged in those processes would never spread into space. Even the devices that form the backbone of modern electronics, from semiconductors to quantum circuits, would fail. The absence of tunneling would be the absence of almost everything we know. Yet tunneling is not merely about survival, it is about possibility. The fact that barriers are never perfect means the universe is not a cage of certainty, but a playground of chance. Each barrier is a suggestion, not a decree. Each wall is porous, however faintly. This openness makes reality dynamic, ever-changing, alive with transitions that classical physics would forbid. Physicists often describe tunneling with analogies, but none fully capture its nature. Some speak of ghosts passing through walls, others of dice rolling with improbable results. But the truth is stranger. It is not that the particle sneaks through unseen, it is that the particle is not confined to a single place until it is measured. It exists as a wave spread across possibilities, and that wave simply allows it to be found beyond the barrier. What we call tunneling is the universe revealing that the forbidden is only improbable, never impossible. Experiments continue to probe the details. In the laboratory, scientists trap atoms in potential wells and measure how long it takes them to escape. They build junctions so small that electrons can only pass by tunneling, and they measure the currents that flow. Every result confirms the predictions. The exponential laws hold, the probabilities align, and tunneling remains one of the most reliable features of quantum mechanics. Still, mystery lingers in the way tunneling relates to time. Some experiments suggest that tunneling is effectively instantaneous, as if the particle does not experience the barrier at all. Others suggest subtle delays that depend on how the measurement is framed, but none of these results resemble classical travel. The consensus is clear. Tunneling is not a journey, but a probability. The particle does not pass through the wall does not crumble. Instead, reality allows the particle to be found on the far side because its wave function never truly stopped there. This challenges our deepest intuitions. We are used to thinking in paths, motions, and causes. Tunneling asks us to think in possibilities, wave functions, and probabilities. It is not that cause and effect are broken, it is that they are rewritten in the language of chance. The barrier resists but does not forbid, the wall denies but does not exclude. The impossible is always only improbable, and improbability is part of the fabric of the cosmos. This realization prepares us for a profound transition. If tunneling is not just an abstract principle, but a force that powers the stars, then we must carry our story outward. The next step is to leave the laboratory and turn our gaze to the heart of the Sunday. There, in the searing furnace of hydrogen, tunneling is not an oddity but the very reason the sky is bright. Without it, the cosmos would be silent and cold. With it, the universe burns with light. The sun shines with a steady brilliance that has warmed Earth for billions of years, and yet the secret of its light defies classical logic. At its core lies a furnace of unimaginable pressure and heat. Temperatures climb to more than 15 million degrees Celsius. Densities reach more than 100 times that of water, and hydrogen atoms crowd so closely that they jostle like dancers, packed onto a floor with no room to move. Under such conditions, it would seem natural for the protons in those hydrogen atoms to fuse together, releasing energy in the process. But here, classical physics raises its voice and says no. Each proton carries a positive electric charge, and like charges repel with fierce strength. The closer two protons come, the stronger the repulsion becomes. At the distances where fusion must occur, the electric barrier is so steep that even the heat of the solar core is not enough to force protons together. By the rules of Newton and Maxwell, the sun should never have ignited. Its core should remain a seething but impotent mass of hydrogen, glowing faintly from gravitational compression, but never burning with nuclear fire. Yet the sun does burn. It burns steadily, reliably, with a light that has bathed Earth for 4.5 billion years. It shines so strongly that every second it radiates more energy than humanity has ever produced in its entire history. How can this be? if the protons lack the strength to fuse? The answer is tunneling. In the quantum world, protons are not rigid spheres colliding like billiard balls. They are waves, smeared across space, their positions uncertain, their identities blending into probability. When two protons approach in the solar core, their waves overlap. Classically, the barrier of electric repulsion would stop them cold, but quantum mechanics allows their wave functions to seep through that barrier. Most of the time, the overlap decays away before reaching the region where the strong nuclear force takes over, but not always. Sometimes the wave survives long enough for the protons to be discovered inside the barrier, close enough for the strong force to bind them together. This is the miracle of the Sunday fusion occurs not because the protons have enough thermal energy to climb the electric hill, but because their probability waves tunnel through it. The sun is not a classical furnace, it is a quantum furnace. Its light is born from the improbable, repeated countless times each second across its immense core. The mathematics shows how this works. The probability of two protons fusing depends on both the temperature of the core and the tunneling chance through the electric barrier. At 15 million degrees Celsius, the average proton has far too little energy to cross the barrier directly. But the exponential decay of the wave function inside the barrier gives each encounter a tiny probability of success. Multiply that tiny probability by the immense number of protons colliding every instant in the dense solar core, and fusion becomes inevitable. This is why the sun shines so steadily. It does not rely on rare miracles. It relies on probabilities, so vast in repetition that they become certainty. Each second, about 600 million tons of hydrogen fuse into helium, releasing energy that streams outward as sunlight. Without tunneling, none of those fusions would occur. With tunneling, the sun burns with a brilliance that shapes the entire solar system. The lesson is humbling. The warmth on your skin when you stand in sunlight is a direct consequence of quantum tunneling. The photons that nourish plants, that drive weather, that illuminate the day, were born from protons that fused because their wave functions overlapped, where classical physics said they could not. The impossible is not a rare exception. It is the reason life exists. And the sun is not alone. Every star in the night sky owes its light to tunneling. From the smallest red dwarf to the most massive blue giant, fusion in stellar cores depends on quantum mechanics. Without tunneling, the universe would be filled with dark gas clouds, lifeless and cold. With it, galaxies blaze, elements form, and life becomes possible. But tunneling does more than power stars. It also fuels the technologies we build on Earth. Just as the sun depends on tunneling to shine, human inventions rely on tunneling to function. To see this, we must leave the heart of the cosmos and enter the world of laboratories, where scientists harness tunneling in microscopes, diodes, and computers. There, the same principle that powers the stars becomes the foundation of modern technology. The deeper we look into the heart of the sun, the more astonishing the story becomes. The first step in the chain of fusion is the meeting of two lonely protons. By classical reckoning, the chance of this union should be so small that the sun would never ignite in the lifetime of the universe. But the quantum world is not bound by such stern decrees. Thanks to tunneling, some pairs of protons succeed, slipping through the electric barrier and finding themselves close enough for the strong nuclear force to act. When this happens, the strong force binds the two protons together, but there is a complication. Two protons alone cannot form a stable nucleus. To resolve this, one of the protons must transform into a neutron through the weak nuclear force, emitting a positron and a neutrino in the process. What remains is a deuterium nucleus, a union of one proton and one neutron. This is the first spark of fusion, the unlikely birth that makes all the rest possible. From there, the chain reaction unfolds. The deuterium nucleus can fuse with another proton, creating helium-3. Two helium-3 nuclei can collide, producing helium-4 and releasing two protons back into the sea of hydrogen. Step by step, the sun converts hydrogen into helium, and in the process, it releases energy in the form of photons. These photons scatter and ricochet inside the dense solar plasma for thousands of years before finally escaping into space as the sunlight we see. The numbers are staggering. Every second, about 4 million tons of matter are converted into energy in the core of the Sunday. This energy flows outward, sustaining the delicate balance between gravity pulling the star inward and pressure pushing outward. Without tunneling, that balance would never be achieved. The sun would collapse under its own weight, a failed star unable to ignite. Instead, tunneling makes the improbable common, and the sun burns steadily across billions of years. The same principle applies across the cosmos. Red dwarfs, the most numerous stars in the universe, rely on tunneling to fuse hydrogen at much cooler temperatures than our Sunday. Massive stars, which burn through their fuel in only a few million years, also depend on tunneling to sustain the furious rates of fusion that light their brilliance. Even exotic stars at the edge of stability draw their energy from quantum mechanics. Tunneling is not just a quirk of one star, it is the universal engine of starlight. This makes the night sky itself a testimony to tunneling. Each twinkle of a distant star is a reminder that the improbable is at work everywhere. Without tunneling, the heavens would be dark, the galaxies would be invisible, and life would never find the energy it needs to thrive. What appears eternal and inevitable, the light of stars, is actually born of chance, repeated countless times, and it does not stop with starlight. The elements that form planets and living beings also owe their existence to tunneling. Fusion inside stars produces helium, carbon, oxygen, and heavier elements. Later, when massive stars die in supernova explosions, those elements are scattered across space. Earth itself is built from atoms forged in such stars, atoms that only exist because tunneling made fusion possible. Every breath you take, every molecule in your body, is a relic of tunneling inside ancient stellar furnaces. This understanding transforms the way we see the Sunday. It is not merely a ball of gas burning in the sky. It is a quantum engine, a vast machine powered by probabilities. Its light is the sum of innumerable tunneling events, each one improbable, but together inevitable. Life on Earth is therefore not only warmed by the sun, but also born from the improbable generosity of tunneling. Yet, even as we marvel at the cosmic scale of tunneling, we must not forget that the same principle touches the world of human invention. The sun shows us that tunneling fuels the stars, but in laboratories on Earth, scientists harness tunneling to explore the tiniest structures of matter and to build devices that shape our everyday lives. From microscopes that see atoms to circuits that guide our technology, tunneling is as close to us as the light in our homes, and so the story carries us forward. From the heart of the sun to the surface of a microchip, tunneling reveals itself not as a rare oddity, but as a thread that runs through all of existence. The same phenomenon that powers the cosmos also powers our machines. To see this, we must leave the fiery core of stars and step into the quiet precision of human technology, where tunneling becomes a tool as practical as it is profound. The sunlight that streams through our skies is the sum of countless improbable events. Each proton fusion in the solar core is so unlikely, so fiercely resisted by the electric barrier, that without quantum tunneling, it would never occur. But tunneling gives the universe a loophole, and through that loophole pours the energy that lights the cosmos. Think of the scale. In every second, about 10 to the power of 56 protons attempt collisions in the core of the Sunday. The vast majority repel and drift apart, their waves failing to overlap enough to reach the embrace of the strong force. But a tiny fraction succeed, slipping through the barrier by tunneling. That fraction is enough to release 4 million tons of energy every second, converted directly from matter into light and heat. It is enough to sustain the balance of the sun, keeping it from collapsing under its own weight. It is enough to warm the earth, to power photosynthesis, to drive weather, and to allow life to flourish. When we stand under the sun, it feels constant, steady, eternal. But behind that steadiness lies a dance of chance. Each fusion event is improbable, each success a triumph against the odds. Yet the sheer number of attempts ensures that improbability becomes inevitability. The sun is a reminder that nature does not need certainties. It needs only possibilities, repeated across unimaginable scales. This insight reshapes how we think about the cosmos. Every star is a quantum engine, the faint red dwarf glowing dimly at the edge of the galaxy, the blazing blue giant burning itself out in a few million years, the ordinary sun around which we orbit all shine, because tunneling turns the impossible into the inevitable. The night sky, filled with stars, is a map of tunneling at work. The consequences go beyond starlight. Fusion not only produces energy but also forges the elements. Carbon, oxygen, nitrogen, and the building blocks of life emerge from nuclear furnaces powered by tunneling. Later, when stars die in supernova explosions, Those elements are scattered through space, seeding planets, oceans, and eventually living beings. You and I exist because protons tunneled in ancient stars. Every breath, every heartbeat is a ripple of that improbable process. This realization is both scientific and poetic. It shows us that life is not a trivial accident, but the outcome of laws that allow the improbable. It also shows us that the universe is richer than our classical imaginations once believed. Instead of rigid certainties, it is built on possibilities, and tunneling is one of the most profound expressions of that truth. But the story of tunneling is not confined to the vast furnaces of the stars. It also plays out on scales small enough to fit in the palm of your hand. Just as tunneling allows protons to fuse in stellar cores, it allows electrons to leap across barriers in human devices. From microscopes that see atoms to circuits that compute with quantum states, tunneling is as much a tool of modern science as it is a power of the cosmos. And so our journey continues, carrying us from the heart of the sun to the heart of human technology. The same principle that fuels the stars now fuels our machines, proving once again that the improbable is not rare, but everywhere. When scientists first uncovered the reality of tunneling, it seemed like a curiosity of the quantum world, a trick of mathematics that played out in stars and nuclei, but had little to do with daily life. Yet as the 20th century unfolded, engineers began to realize that tunneling was not only real but useful. The very strangeness that allows particles to pass through barriers became a tool that could be harnessed, measured, and built into machines. Today, tunneling is at the heart of some of the most remarkable technologies on Earth. One of the most striking examples is the scanning tunneling microscope. At first glance, the idea sounds impossible. How could anyone hope to see individual atoms, objects, far smaller than the wavelength of light? Ordinary microscopes cannot resolve them, no matter how powerful their lenses. But tunneling provided another way. In the early 1980s, scientists discovered that if you bring an extremely sharp metal tip close to the surface of a material, so close that the gap is only a few atoms wide, electrons can tunnel across the gap. The current that flows depends exquisitely on the distance between the tip and the atoms below. By moving the tip back and forth while measuring this tunneling current, scientists can map the surface atom by atom, creating images that reveal the very building blocks of matter. For the first time in history, humanity could not only infer the existence of atoms but actually see them. The scanning tunneling microscope showed us individual atoms, arranged in lattices, clusters, and patterns. It let us push atoms around, building tiny structures one by one, arranging the quantum world like a sandbox of the unimaginably small. This was not only a triumph of science but also a direct use of tunneling as a tool. The electrons that leap across the gap are performing the same improbable trick that fuels the sun, only now in service of human curiosity. Tunneling also powers a class of devices known as tunnel diodes. In ordinary diodes, current flows in only one direction, blocked in the other. But in tunnel diodes, the barrier between two regions of semiconductor is so thin that electrons can tunnel through in ways that produce unusual behavior. At certain voltages, the current actually decreases as the voltage increases, a phenomenon known as negative resistance. This oddity makes tunnel diodes incredibly fast, capable of switching at speeds useful for high-frequency electronics. They were among the first quantum devices, proving that tunneling could be engineered into circuits, not just observed in nature. As technology advanced, tunneling became unavoidable. In modern transistors, the barriers that separate electrons are now only a few atoms thick. At such scales, tunneling is no longer a rare effect, it dominates. Engineers designing microchips must account for electrons tunneling across barriers and leaking through gates. What was once an exotic phenomenon is now a daily challenge in the design of computers and phones. Quantum mechanics has slipped into the fabric of everyday life, hidden inside the processes that power our world. And tunneling may hold the key to the next revolution. Quantum computers, machines that promise to solve problems beyond the reach of classical processors, rely on delicate quantum states. Tunneling plays a role in their operation, both as a tool and as a challenge. Certain types of quantum bits, or qubits, use tunneling as a way for particles to switch states. Other designs must contend with unwanted tunneling that disrupts coherence. In both cases, the mastery of tunneling is central to building machines that could transform science, medicine, and technology. This is the great irony. What began as a mathematical curiosity has become a practical necessity. The same effect that lets protons fuse in the sun now lets us image atoms, design circuits, and dream of quantum computers. Tunneling is not only a phenomenon of the stars and nuclei, it is a phenomenon of our devices, our laboratories, our daily lives. And yet, the story does not end with human technology. Tunneling also shapes the natural world beyond stars. It governs how unstable nuclei decay, allowing particles to escape even when trapped behind powerful nuclear barriers. This process, known as radioactive decay, is one of the clearest and most dramatic manifestations of tunneling. It is a phenomenon that not only explains the stability of matter, but also fuels the heat of Earth itself. To understand tunneling in its fullest depth, we must now step from the realm of microscopes and circuits into the heart of the atomic nucleus, where tunneling opens a path to nothingness. The scanning tunneling microscope was more than just an invention, it was a revelation. Before its arrival, atoms were abstractions. Scientists knew they existed through indirect evidence, from the tracks they left in chambers and the way they explained chemical bonds. But to see them directly was like lifting a veil from nature itself. When the first images appeared in the early 1980s, showing neat arrays of atoms on a surface, the world of the quantum suddenly became visible. Each tiny peak in the image corresponded to a single atom, mapped by the tunneling of electrons across a gap too small for light to cross. The precision was astonishing. A movement of the microscope tip by a fraction of a nanometer could change the tunneling current dramatically, revealing the presence or absence of a single atom. By carefully scanning, scientists could build three-dimensional pictures of atomic landscapes, like mountain ranges of the microscopic world. Even more astonishing, the same tip could be used to push atoms around, one by one, arranging them into patterns or structures. In one famous demonstration, researchers spelled out the letters of a company name with atoms, showing that tunneling had given humanity the power not just to see atoms, but to manipulate them. The implications were profound. Whole new fields of nanotechnology and materials science opened, allowing researchers to design structures, atom by atom. Molecules could be studied not as abstract chemical formulas, but as arrangements of atoms on a surface. Quantum tunneling had become not just a phenomenon, but a practical tool, extending human vision and touch into realms once thought unreachable. But tunneling also shaped electronics in subtler ways. In tunnel diodes, the peculiar property of negative resistance became a resource. By harnessing tunneling currents, engineers created devices that could switch faster than traditional components, operating at frequencies beyond the reach of ordinary circuits. Although tunnel diodes are not as common today as other semiconductor components, they marked an early step in the deliberate use of tunneling as a design principle. As microelectronics advanced, tunneling became less a choice and more an inevitability. The transistors that form the basis of modern microchips shrank to scales of just a few nanometers. At those dimensions, the barriers that once confined electrons were so thin that tunneling currents could not be ignored. What once seemed like an exotic effect became a daily engineering problem. Too much tunneling meant that electrons leaked through circuits, wasting energy and generating heat. Too little tunneling meant that devices could not operate at the speeds required. Engineers found themselves working with tunneling whether they wanted to or not, adjusting materials and designs to balance its effects. This convergence of quantum mechanics and technology showed a truth that still resonates. We do not live in a classical world with quantum rules tucked away in corners. We live in a quantum world, and as our tools become smaller and finer, we collide with that reality more and more directly. The chips in our computers, the memories in our phones, the devices that drive our daily lives, all depend on engineers who understand tunneling, even if most people remain unaware that the principle of the sun's fusion is also at work in their electronics. The frontier is even more ambitious. Quantum computing seeks to build machines that exploit quantum rules directly, using superposition and entanglement to perform calculations no classical computer could manage. In these machines, tunneling appears both as an ally and an adversary. Certain designs rely on tunneling to allow qubits to shift between states, encoding information in ways that transcend the binary logic of ones and zeros. Other designs must battle against unwanted tunneling, which can disrupt delicate quantum states and destroy information. Mastery of tunneling becomes not just useful, but essential, for without it, the promise of quantum computing remains out of reach. Thus, tunneling has become a symbol of the strange partnership between humanity and the quantum world. It is not only a law of physics, but a resource, a challenge, and an opportunity. It powers microscopes that reveal atoms, diodes that switch at high frequencies, and computers that may one day transform every aspect of life. The improbable leap across barriers has become part of the fabric of modern civilization. Yet, as impressive as this is, tunneling is not confined to machines or laboratories. It is also one of the most powerful forces shaping nature itself. Inside the hearts of unstable atoms, tunneling governs how particles escape, creating the phenomenon of radioactivity. This is tunneling at its most dramatic, as particles break free from nuclear prisons in defiance of classical barriers. To follow the story of tunneling, we must now step into that hidden world of nuclear decay, where probability guides the transformation of matter itself. The story of tunneling in technology is also a story of limits. For decades, engineers made computers faster and smaller by shrinking transistors, packing more of them into each chip. The principle seemed unstoppable, a march toward infinite speed and power. But as those transistors reached sizes of only a few nanometers, tunneling emerged as a barrier. Electrons began slipping through layers that were supposed to confine them, leaking into places they should not go. Circuits designed to be perfect switches instead allowed tiny but relentless currents, wasting energy and heating the chip. This was not a flaw in manufacturing. It was a fundamental law of physics. Barriers a few atoms thick are no longer barriers at all. They are invitations to tunneling. The very success of miniaturization brought engineers face to face with the quantum world. In response, new materials were invented, new architectures designed, and new strategies developed to manage tunneling. The effort continues today, with every generation of processors balancing on the edge of quantum leakage. But tunneling is not only a problem to be solved, it is also a possibility to be embraced. In quantum computing, tunneling is not a nuisance, but a resource. Qubits, the building blocks of these machines, often rely on tunneling to switch states. Superconducting qubits, for example, use pairs of electrons that can tunnel across tiny gaps, maintaining coherence long enough to perform computations. Quantum annealers, another design, use tunneling deliberately to find solutions by allowing systems to escape local traps in their energy landscape. In these machines, tunneling is not avoided. It is the very heart of the computation. The idea that electrons tunneling through barriers can solve problems for us may sound surreal, but it is real. Companies and research groups have already built prototypes that perform tasks using this principle. The machines are fragile, delicate, and still in their infancy, but they are proof that tunneling is not just a curiosity of nature or a challenge for engineers. It is a tool with the potential to redefine what technology can do. This is the arc of tunneling in human hands. It began as a strange prediction of mathematics, confirmed in the laboratory. It became a tool for imaging atoms, a challenge for microelectronics, and a resource for quantum computing. It shows us that the boundary between the possible and the impossible is not fixed, but porous. Just as particles slip through barriers, humanity has slipped through its own limitations by harnessing tunneling as a principle of design. And yet, as extraordinary as these achievements are, tunneling is not limited to human invention. It is not something we created or discovered in the sense of novelty. It is something that has been part of the universe since the beginning. Long before humans built microscopes or computers, tunneling shaped the fate of stars, the formation of elements, and the decay of atoms. This brings us to one of the most profound manifestations of tunneling, nuclear decay. In the heart of unstable atoms, particles are bound by powerful nuclear forces and repelled by electric barriers. Classical physics insists they should remain trapped forever, yet they do not. They escape, not by breaking the rules, but by tunneling through the barriers that hold them. Radioactivity is tunneling written into the very fabric of matter, transforming atoms into new forms and releasing energy that warms planets, shapes geology, and fuels life. To understand this, we must step beyond devices and circuits into the nucleus itself. There, tunneling opens the door to transformation, allowing particles to emerge from confinement in ways that define the very stability of matter. It is tunneling at its rawest and most dramatic, a reminder that the universe itself is always in motion, always leaking possibilities through the barriers that seem absolute. At the heart of every atom lies the nucleus, a compact cluster of protons and neutrons bound together by the strongest force in nature. The strong nuclear force pulls these particles into a tight embrace, but the protons resist with their electric repulsion, each positive charge pushing against the others. This fragile balance is what holds matter together. But in many nuclei, the balance is imperfect. They are unstable, trembling on the edge of change, waiting for a chance to transform. Classical physics tells us that such unstable nuclei should be eternal prisons. A particle inside, like an alpha particle made of 2 protons and 2 neutrons, is trapped behind an immense barrier of electric repulsion. The energy required to climb over this barrier is immense, far greater than the particle possesses. By every classical rule, escape is impossible. The alpha particle should remain locked inside the nucleus forever, and radioactive decay should never occur. Yet radioactive decay does occur, and it does so with a reliability that has shaped the history of science. Elements like uranium, thorium, and radium radiate with steady persistence, shedding alpha particles that fly outward with measurable energy. Their half-lives, the time it takes for half of a sample to decay, are predictable, stretching from fractions of a second to billions of years. Radioactivity is not random chaos. It is statistical order, governed by laws that can be measured and trusted. The secret, once again, is tunneling. The alpha particle inside the nucleus is not a prisoner pacing behind impenetrable walls. It is a wave of probability, pressing against the electric barrier. Most of the time, the wave reflects inward, confined by the nuclear potential. But part of the wave seeps into the barrier itself, decaying as it goes. If the barrier is thin enough, or the wave energetic enough, a trace of it will survive to the far side. When that happens, the alpha particle appears outside the nucleus, free at last, carrying energy into the wider world. This is why uranium decays into thorium, why radium emits glowing particles, why Earth itself is warmed by the slow release of radioactive heat deep underground. Tunneling is not a rare anomaly. It is the mechanism by which unstable matter transforms, reshaping itself through the leakage of probability. The mathematics of alpha decay is one of the triumphs of quantum mechanics. In the 1920s, George Gamow applied the principles of tunneling to explain the observed lifetimes of radioactive nuclei. His calculations matched the data with astonishing accuracy. Nuclei that would be eternally stable in the classical world had finite half-lives in the quantum world, their stability determined not by brute force, but by the delicate balance of tunneling probabilities. This revelation transformed nuclear physics. It showed that decay was not a mysterious act of instability, but a predictable outcome of quantum mechanics. The half-life of an element could be explained by the height and thickness of the barrier confining the alpha particle, and by the energy of the particle itself. A higher barrier meant slower decay, a thinner barrier meant faster decay. What looked like chance was revealed as mathematics. Yet, the process remains probabilistic at its core. We cannot say which atom in a sample will decay at which moment. We can only say that half will decay in a given time, and the other half will remain. This mixture of precision and uncertainty is the signature of quantum mechanics. It is why radioactivity is both reliable and unpredictable, both statistical and mysterious. The consequences ripple outward into the cosmos. The heat that keeps Earth's core molten comes in part from radioactive decay, itself a product of tunneling. Without it, the planet's interior would have cooled long ago, and plate tectonics, volcanoes, and the magnetic field that shields us from cosmic rays might never have existed. Life on Earth depends not only on the sun's tunneling-driven fusion, but also on the tunneling-driven decay of elements deep within. This is tunneling at its starkest. Inside the nucleus, particles should never escape, yet they do, because probability finds a way. What classical physics forbids, quantum mechanics allows, not by breaking laws, but by rewriting them in the language of waves and chances. And this is not the end of the story. Radioactivity is only one face of tunneling in nuclei. Other forms of decay, from beta decay to proton emission, also carry the mark of quantum mechanics. Each reveals the porousness of barriers, the openness of the universe to possibility. And beyond the physics, these decays touch philosophy itself. They show us that stability is never absolute, that even the most solid forms of matter are only temporary, and that change is built into the heart of the cosmos. To follow tunneling further, we must step beyond physics into philosophy. For if particles can tunnel through barriers and atoms can decay through walls of impossibility, what does that say about determinism, about predictability, about the very nature of reality? Tunneling is not only a physical process, it is a philosophical shock. a reminder that the universe is woven from chance as much as from necessity. The mystery of nuclear decay deepens when we consider the way it unfolds over time. Imagine holding a lump of uranium in your hand. You cannot predict which atom will decay in the next second, nor can you influence it. The process is utterly indifferent to observation, untouched by intent. But if you measure 1 billion uranium atoms, you can predict with precision how many will decay in a given span. This duality, unpredictable in the individual, reliable in the collective, is the fingerprint of tunneling at work. The mathematics captures this perfectly. Each atom has a probability per unit time of releasing an alpha particle through tunneling. That probability does not change as the atom grows older. An atom that has existed for 1 billion years is no more or less likely to decay in the next instant than one created yesterday. This is why we describe decay in terms of half-life. After a certain span, half the atoms in a sample will have decayed, half will remain. Wait another half-life, and half of those remaining will decay, and so on, the population dwindling step by step in a graceful exponential decline. This statistical regularity has made radioactive decay one of the most powerful tools in science. By measuring the ratios of parent and daughter isotopes in a rock, geologists can date its age with remarkable accuracy, tracing the history of Earth itself. Archaeologists use the same principle with carbon-14, a radioactive isotope produced in the atmosphere and absorbed by living beings. When a creature dies, the carbon-14 in its body begins to decay, and by measuring how much remains, scientists can determine how long ago it lived. The clocks of tunneling are written into the very bones of history. Yet beneath this usefulness lies a profound strangeness. Why should an atom wait 1 billion years before decaying, and why should it then release an alpha particle in the next moment with no warning? The answer is that the alpha particle inside the nucleus is constantly pressing against the barrier, its wave function seeping into the forbidden region. Each moment carries the same tiny probability that it will appear on the other side. Most of the time, the probability fails. Occasionally, it succeeds. Over billions of atoms and billions of years, the statistics unfold into a smooth law of half-life. This means that even the stability of matter is only a matter of probability. The iron in your blood, the calcium in your bones, the silicon in the rocks beneath your feet all are stable only because their nuclei are not prone to tunneling in ordinary spans of time. But even they are not absolutely eternal. Given enough time, every configuration of matter has a chance of changing, however small. The solidity we take for granted is really a balance of probabilities, not an unbreakable law. The consequences for Earth are immense. The radioactive decay of elements such as uranium, thorium, and potassium, deep within the planet, releases heat that keeps the core molten. This heat drives convection, which moves tectonic plates and fuels volcanic eruptions. Without it, Earth's surface would be geologically dead, a frozen crust without mountains or oceans. The magnetic field that shields us from cosmic radiation depends on this molten core, and without it, life would be exposed to the full fury of space. All of this tectonics, volcanism, magnetism, habitability flows from the quantum tunneling of particles inside unstable nuclei. It is a reminder that tunneling is not confined to laboratories or stars. It shapes the very world we walk upon. Every landscape, every mountain, every ocean owes its existence in part to the steady ticking of radioactive decay, itself made possible by particles tunneling through barriers they should never cross. And yet, tunneling in nuclear decay is not only a physical truth, but a philosophical one. It tells us that certainty is an illusion, that even the most solid matter is not truly fixed. It tells us that the future is not written in inevitabilities but in probabilities. It forces us to rethink what it means for something to be real, stable, or lasting. As we confront these questions, we begin to see that tunneling is more than a mechanism. It is a challenge to our understanding of the universe. The decay of atoms through tunneling is not just a process of physics. It is a message that reality itself is probabilistic, that chance is not a weakness of our knowledge, but a fundamental feature of existence. And so the path of tunneling carries us onward. From the predictable decay of nuclei, we are led into the unpredictable terrain of philosophy. What does it mean to live in a universe where walls are porous, where stability is temporary, where certainty is replaced by possibility? The shock of tunneling is not only scientific but philosophical, and to explore it, we must step beyond physics into questions of determinism, chance, and free will. The nucleus, with all its immense energies and binding forces, seems like the last place where chance should rule. Yet the reality of tunneling makes clear that even here, at the core of matter, nothing is absolute. When we speak of a nucleus as stable, what we truly mean is that the probability of tunneling within it is vanishingly small. When we call a nucleus unstable, what we mean is that tunneling will eventually occur, and when it does, the atom will transform. There is no guiding hand choosing the moment, no hidden mechanism waiting for a signal. There is only the relentless mathematics of probability, ticking like a cosmic clock that never strikes in certainty but always in chance. This is why radioactive decay feels like a tunnel to nothingness. Inside the nucleus, the alpha particle is bound by one of the most powerful forces in the universe. By classical reckoning, it should remain trapped forever. Yet tunneling writes another story. It allows the particle to seep beyond the barrier, to emerge into open space, leaving the nucleus diminished, altered, reborn as another element. The atom does not shatter violently from within, it simply changes, quietly, by the steady whisper of probability. For humans, the consequences have been immense. The discovery of radioactivity at the end of the 19th century transformed science and society. It provided tools for probing the age of Earth, for treating diseases with radiation, for developing nuclear power, and for building weapons of staggering destructive power. All of this rests on the same foundation: particles slipping through barriers they should never cross, tunneling from confinement into freedom. Yet beyond the practical lies the philosophical. If the most solid structures of matter are subject to tunneling, then what does stability truly mean? If every atom carries within it the faint chance of transformation, then permanence itself is an illusion. We live in a universe where change is not an accident but a rule, written into the mathematics of quantum mechanics. Tunneling reminds us that nothing is eternal, not stars, not elements, not even the ground beneath our feet. This challenges the classical dream of determinism, the vision of a universe that unfolds like a clockwork, with each moment dictated by the last. Tunneling shows us a universe where barriers are porous, where certainty dissolves into probability, where the impossible is only improbable. It shows us a cosmos, not of fixed destiny, but of possibilities realized through chance. And this is where tunneling steps beyond physics into philosophy. It forces us to question the nature of causality, the meaning of chance, and the role of probability in shaping reality. If the universe is built not from certainties but from waves of possibility, then what does that say about free will, about determinism, about the predictability of the future? The alpha particle tunneling from a nucleus is not only a physical event, it is a metaphor for the porousness of reality itself. The walls we imagine as solid are not truly solid, the rules we believe to be absolute are not truly absolute. Reality is not a fortress, but a field of chances. And so, as we leave the nuclear realm, our journey carries us into the realm of ideas. The next chapter is not about stars or atoms, but about philosophy. It is about how tunneling reshapes our understanding of the universe, how it overturns the clockwork vision of determinism, and how it suggests that chance, not certainty, lies at the heart of existence. The discovery of tunneling was not only a turning point in physics, it was also a turning point in philosophy. For centuries, science had carried the dream of determinism, the belief that, if one knew all the positions and motions of particles at one moment, then the future could be calculated with perfect precision. It was the vision of a clockwork universe, each tick of reality following inevitably from the last. Newton's laws, so exact and predictable, seemed to confirm this dream. The universe was a machine, and the human mind, given enough knowledge, could read its future like a book. But tunneling shattered that vision. Here was a process where particles trapped behind barriers could escape without cause, in the classical sense. No force pushed them over the wall, no hidden mechanism waited for the right signal. They escaped because probability allowed them to, and because the quantum wave that defined them did not respect absolute boundaries. At the level of individual atoms, no one could say when the event would occur. Only probabilities could be given. The universe, once thought to be a clock, revealed itself as a casino, each outcome weighted by chance. This was not a comfortable revelation. Philosophers and physicists alike struggled with its implications. If the future was not determined, then what was the nature of reality itself? Was it a chain of causes leading to effects, or was it a tapestry of probabilities woven into being as time unfolded? Tunneling made clear that even the most fundamental processes, the transformations of atoms and the burning of stars, depended on chance. It showed that uncertainty was not a limit of knowledge but a law of nature. To appreciate the shock, imagine an unstable nucleus, waiting to emit an alpha particle. Classical physics would insist it could never escape, or if it did, there must be some hidden trigger. But quantum mechanics says otherwise. At any moment, the alpha particle may appear outside the barrier. No trigger, no warning, no hidden variable we can measure, just probability, realized without cause. Multiply this across the universe, and determinism dissolves. The cosmos is not a story already written, but a story being told, moment by moment, each line chosen from a script of possibilities. This strikes at the heart of one of humanity's oldest questions. Do we live in a universe of necessity or of freedom? If every motion were predetermined, then free will would be an illusion, choice nothing more than the unfolding of initial conditions. But if chance plays a role, then the universe is open, not closed. Tunneling suggests that the world is not locked, that chance is built into the foundation of matter itself. This does not prove that human free will exists, but it does prove that the universe is not chained to destiny. And yet, tunneling also teaches humility. For while chance exists, it is not chaos. Probabilities can be calculated, half-lives measured, stellar lifetimes predicted. The universe is not random in the sense of disorder. It is probabilistic in the sense of weighted outcomes. This balance between order and chance is what makes reality both reliable and surprising. Stars shine steadily, yet atoms decay unpredictably. Life evolves with patterns, yet every mutation is an accident of chance. The universe is a harmony between necessity and possibility, between law and freedom. This is the philosophical shock of tunneling. It breaks the dream of absolute determinism and replaces it with something subtler, something stranger, a universe where laws still hold, but their outcomes are probabilistic, a universe where certainty is replaced by possibility, where stability is only temporary, and where the impossible is always just improbable. And this shock does not remain confined to the realm of thought. It echoes into every field of science and philosophy. It challenges the way we think about causality, about time, about existence itself. It forces us to ask whether the future is open or closed, whether reality is fixed or fluid, whether chance is an illusion or the deepest truth. To follow this path is to enter a new territory, one where physics and philosophy blur. For tunneling is not only a law of matter, it is a message about the nature of the universe. And as we listen to that message, we begin to glimpse even deeper mysteries, where tunneling reaches beyond matter and energy, touching the very fabric of the vacuum itself. The philosophical shock of tunneling lies in the way it reshapes our idea of certainty. In the old vision of the clockwork cosmos, the present contained the seeds of the future in absolute form. Every orbit of a planet, every swing of a pendulum, every collision of stones followed inevitability. If one had perfect knowledge, as the mathematician Pierre Laplace once imagined, one could compute the entire fate of the universe from a single instant. Quantum mechanics, and tunneling in particular, silences that dream. The particle in the nucleus that escapes by tunneling is not predicted in time. No matter how much knowledge we gather, we cannot say when it will leave. The most we can say is that within a certain span, half of them will have done so. We exchange inevitability for probability, certainty for chance. This is not because of ignorance, not because we are blind to hidden causes. It is because the universe itself is probabilistic at its foundation. This realization unsettled the greatest minds of the 20th century. Albert Einstein, whose theories reshaped time and space, resisted it with the famous protest that God does not play dice with the universe. But experiments have confirmed again and again that dice are indeed rolled, that tunneling and other quantum events are not the shadows of hidden certainties, but the expression of genuine chance. The philosophical dream of determinism cracked, and through that crack poured a new understanding of reality. For some, this was liberating. It meant the universe was not a script already written, but a canvas still being painted. It meant that novelty was real, that the future could surprise, even in principle. For others, it was unsettling. How can science be trusted if events are ruled by chance? Yet the paradox of tunneling is that chance and reliability coexist. We cannot predict which atom will decay, but we can predict, with extraordinary precision, how many atoms in a sample will decay in a given time. We cannot predict which particle will tunnel through a barrier, but we can predict the probabilities of tunneling with equations that match experiment to many decimal places. This coexistence of chance and law is what makes quantum mechanics, and tunneling especially, so powerful. It shows that uncertainty does not mean chaos. The universe remains lawful, but its laws are written in the language of probabilities rather than absolutes. The future is not fixed, but neither is it formless. It is sculpted by likelihood, by distributions, by the mathematics of waves and chances. This redefines causality itself. In the classical view, every event had a cause, and the chain of causes stretched back infinitely. In the quantum view, some events happen not because of a cause in the classical sense, but because the probability allowed it. The alpha particle leaves the nucleus not because it was pushed, but because its wave function leaked through the barrier. The star shines not because protons had the energy to fuse, but because tunneling allowed their waves to overlap. These events are not uncaused, they follow laws, but their laws are probabilistic rather than deterministic. For philosophy, this is a revolution. It blurs the line between necessity and freedom, between fate and chance. It raises questions about free will, about whether human decisions are the unfolding of physical laws or the expression of probabilistic processes in the brain. It suggests that reality itself is a blend of order and possibility, that existence is not a path, but a spectrum of potential outcomes, realized moment by moment. And tunneling makes this truth vivid. It shows us that walls are never absolute, that impossibility is an illusion, that stability itself is temporary. It shows us that the universe is built on chance, not as an afterthought, but as a foundation. This is why tunneling is not only a scientific fact, but a philosophical shock. It overturns centuries of certainty and replaces them with a vision of reality as porous, probabilistic, and open. As unsettling as this may be, it also prepares us for deeper mysteries. For if tunneling is not limited to matter and energy, but also touches the vacuum itself, then the implications are even more profound. In the fabric of empty space, particles flicker in and out, tunneling from nothingness into existence before vanishing again. This is where the story of tunneling leads us next, into the strange and restless vacuum where reality itself is never still. At the deepest level, tunneling teaches us that reality is not built of certainties, but of possibilities. Each particle is not a fixed point, but a wave of potential, and each event is not a predetermined outcome, but a probability waiting to be realized. This view unsettles the old dream of determinism, but it also enriches our understanding. The universe is not a closed machine, grinding out its fate with mechanical inevitability. It is an open process, alive with the interplay of chance and law. This openness reframes how we think about time and the future. In a deterministic universe, the future is already written, hidden but fixed, waiting only to be revealed. In a probabilistic universe, the future is not written until it arrives. It emerges from the roll of quantum dice, from the collapse of wave functions, from tunneling events that allow the impossible to become real. This does not mean the future is shapeless or arbitrary. The laws of quantum mechanics give it structure, shaping probabilities with precision, but within that structure, the actual outcomes remain open, undetermined, until the moment of realization. For human beings, this raises profound questions. If the universe itself is probabilistic, what does that mean for choice, for free will, for the meaning of decision? Are we merely passengers in a sea of chance, or does the openness of reality give us room to steer our own paths? Science cannot answer these questions fully, but tunneling makes them unavoidable. It shows us that determinism is not absolute, that chance is woven into the heart of matter, that the future is not locked. Tunneling also reshapes how we see stability and permanence. The walls we imagine around us, physical, conceptual, philosophical, are never absolute. They are barriers of probability, porous at their edges. Atoms decay, stars shine, and even the vacuum itself seethes with fluctuations, all because tunneling allows what classical physics forbids. This means that the solidity of reality is always provisional, always open to transformation. Nothing is eternal, not stars, not atoms, not even the vacuum of space. And this brings us to the next frontier. For tunneling is not confined to matter bound in stars or nuclei. It also governs the restless fabric of empty space. The vacuum itself, far from being nothing, is alive with fluctuations, with particles tunneling into and out of existence. with energy borrowed and repaid in the blink of time. Black holes evaporate by tunneling. Universes may rise and fall by tunneling. The void is not empty but porous, a stage where possibility flickers in and out. This is where our journey now leads. From the philosophical shock of tunneling in matter, we step into the strangeness of tunneling in the vacuum itself. If particles can tunnel through barriers of matter, then perhaps existence itself can tunnel through the walls of nothingness, reshaping reality in ways that defy imagination. At first glance, the vacuum appears to be the ultimate emptiness. Strip away the air, the dust, the light, even the last stray photon, and what should remain is pure nothingness. Classical physics imagines such a vacuum as a perfect void, a stage without scenery, a blank canvas on which the play of matter and energy could unfold. But the quantum world does not allow such silence. Even when stripped of all particles, the vacuum is restless, seething with fluctuations, alive with possibilities that tunnel into and out of existence. This is the consequence of the uncertainty principle, the rule that forbids absolute stillness. A particle and its energy cannot both be defined with perfect precision. Even in empty space, where no particles should exist, the uncertainty principle allows energy to flicker into being for brief moments. These are the virtual particles, phantoms that appear from the vacuum, live for an instant, and vanish again. They are not illusions but measurable presences, their effects observed in experiments, their signatures written into the fine details of atomic physics. Tunneling plays a central role in this strange theater. When particles appear from the vacuum, they are tunneling from the realm of the impossible into the realm of the possible. Most of the time, the vacuum remains quiet, but at every moment, there is a finite chance that a fluctuation will give rise to a particle-antiparticle pair. For a fleeting instant, they exist, then annihilate, returning their borrowed energy to the void. This borrowing and repaying is permitted precisely because the rules of quantum mechanics allow such tunneling, so long as it happens within the bounds set by uncertainty. The effects of these fluctuations are not subtle. They shift the energy levels of electrons in atoms, an adjustment known as the Lamb shift, which has been measured with exquisite accuracy. They tug on objects placed close together in a vacuum, producing the Casimir effect, a tiny force caused by the pressure of virtual particles between the objects. These are not speculative ideas. They are confirmed features of the quantum world, consequences of the fact that the vacuum is never empty. The most dramatic role of tunneling in the vacuum, however, appears near the edge of black holes. According to classical physics, nothing can escape a black hole. Its gravity bends space so steeply that not even light can climb out. But in the quantum world, the vacuum near the event horizon is alive with fluctuations. Particle-antiparticle pairs appear, as they do everywhere. Normally, they annihilate and vanish, but near the horizon, one particle can fall inward while the other escapes outward. To the universe beyond, it looks as if the black hole is radiating. This is Hawking radiation, a process born of tunneling in the vacuum, predicted in the 1970s, and now one of the pillars of modern theoretical physics. Hawking radiation implies that black holes are not eternal prisons, but slowly evaporating bodies. Over immense timescales, they lose mass, shrink, and eventually vanish. This is tunneling on a cosmic stage, particles escaping from the grip of the strongest gravity through fluctuations in the vacuum. It shows that even the most absolute barriers, the event horizons of black holes, are porous when probability has a say. The implications are staggering. If the vacuum itself is alive with tunneling, then emptiness is not the absence of reality, but its foundation. The structure of the universe depends on these fluctuations, from the forces that shape atoms to the evaporation of black holes. What we call nothing is actually a field of infinite potential, a sea of probabilities where existence and non-existence are separated only by the thinnest of barriers. But the story does not end there. Some theories suggest that tunneling in the vacuum is not only responsible for fluctuations and black hole evaporation, but may also have played a role in the birth of the universe itself. Just as particles can tunnel into existence from the void, entire universes may tunnel from one vacuum state to another, inflating into reality. If so, tunneling is not just a feature of matter within the cosmos, but the very engine of cosmic creation. And so, tunneling once again expands its reach. It is not confined to stars, to atoms, or even to our own universe. It may be the principle by which existence itself arises from emptiness, by which the impossible becomes real, on the grandest scale imaginable. The closer we listen to the vacuum, the less it resembles emptiness, and the more it resembles a restless sea. Virtual particles rise like fleeting ripples on its surface, vanishing before they can be grasped, yet leaving behind subtle marks. One of the clearest of these marks is the Casimir effect, first predicted in the mid-20th century. Imagine two perfectly smooth metal plates, placed extremely close to each other in a vacuum, separated by only a few billionths of a meter. Classical physics would expect nothing unusual between them. Quantum physics insists otherwise. Because the vacuum is filled with fluctuations, waves of energy appear and disappear everywhere. Between the two plates, only certain wavelengths can fit. Outside, all wavelengths are allowed. The imbalance creates a pressure that pushes the plates together, a force born entirely of the vacuum itself. This Casimir force is tiny, but it has been measured with precision, confirming that the vacuum is not empty, but alive. It is a force that comes from nothing, yet it moves matter in the real world. Another example lies hidden within atoms themselves. Electrons orbit their nuclei, not like planets circling a sun, but as probability clouds defined by Schrödinger's equation. Yet careful measurements show that their energy levels are shifted by a small but measurable amount, the Lamb shift. The explanation is that the vacuum around the electron is filled with fluctuations, and these fluctuations alter the energy ever so slightly. What seems like nothing alters the very structure of matter. These phenomena are the fingerprints of tunneling in the vacuum. Virtual particles are not created in the usual sense. They tunnel from impossibility into brief existence, sustained by the uncertainty principle. They live just long enough to have an effect before returning to the void. Without them, atoms would not be what they are, forces would not behave as they do, and the stability of the universe would crumble. Perhaps the most haunting consequence of vacuum tunneling appears in the realm of black holes. The edge of a black hole, the event horizon, is the most extreme barrier in nature. Beyond it, not even light can escape. Yet, the vacuum near this edge is never quiet. Virtual particle pairs appear constantly, tunneling into existence as they do everywhere else. Usually, they annihilate one another, almost instantly. But at the event horizon, one particle can fall inward, while the other escapes outward. To an observer far away, it looks as though the black hole has emitted a particle. To balance the books, the black hole loses a tiny amount of mass. This is Hawking radiation, the astonishing prediction that black holes are not eternal, but evaporate, slowly, over time. The rate is almost imperceptible for stellar black holes, but for smaller ones, it grows stronger. In the far future, when galaxies have dimmed and stars have died, black holes may glow faintly with this radiation before vanishing entirely. The strongest prison in nature, once thought to trap everything forever, proves porous in the face of quantum tunneling. The image is almost poetic. Black holes, those dark engines that consume light and matter, are undone, not by force, but by probability. Their destruction comes not from outside attack, but from the restless vacuum itself, tunneling energy across the event horizon. Even the most absolute barrier in the universe yields to the whisper of possibility. And this realization opens another door. If tunneling can eat away at black holes, if it can make emptiness alive, then perhaps it can also reshape the universe itself. The vacuum may not be fixed, but may tunnel from one state to another, releasing vast amounts of energy. Just as particles tunnel through barriers, entire regions of space might tunnel into new forms, giving birth to universes, or ending existing ones. The vacuum is not nothing. It is a stage on which the greatest dramas of existence unfold, from the tiniest shifts in atomic energy to the evaporation of cosmic giants. It is proof that even where there seems to be emptiness, tunneling ensures there is always possibility. The idea that the vacuum itself can tunnel has perhaps the most profound consequences of all. In quantum field theory, the vacuum is not a single empty state, but a landscape of possibilities. Fields can settle into different configurations, each with its own energy. Our universe exists in one such state, but nothing guarantees it is the lowest possible. If the vacuum is only a local resting place, then in principle, it could tunnel into a deeper one, just as a ball perched in a shallow valley can roll into a deeper valley nearby. This possibility is known as vacuum decay, and it is as terrifying as it is fascinating. If the vacuum were to tunnel into a lower state, the laws of physics themselves would change. Particles would gain new masses, forces would take new forms, chemistry would collapse, and structures from atoms to galaxies would unravel. The transition would expand at nearly the speed of light, rewriting reality as it spread. There would be no warning, no defense, only transformation. Physicists study this not out of fear but out of curiosity, for it teaches us about the stability of the universe. Calculations suggest that our universe may indeed be metastable, perched in a high-energy vacuum that could one day tunnel into a lower one. But the probability is so small that the expected lifetime of our vacuum far exceeds the current age of the cosmos. In human terms, it is safe beyond imagining. In cosmic terms, it is a reminder that even existence itself is governed by probability. This vision connects tunneling to the birth of universes as well as their death. In some models of cosmology, the early universe underwent a period of inflation, expanding at extraordinary speed. That inflation may have ended when the vacuum tunneled into a new state, releasing energy that filled the cosmos with matter and radiation. Some theories suggest this process happens repeatedly, with regions of the multiverse tunneling into new vacua, each one creating a new universe with its own laws of physics. In this picture, our cosmos is just one bubble among countless others, born from a tunneling event in the restless vacuum. Whether or not these ideas prove true, they show the reach of tunneling. What began as a strange quantum effect of particles in laboratories extends to the largest scales imaginable. Tunneling allows the sun to shine, allows nuclei to decay, allows black holes to evaporate, and perhaps even allows universes to be born and to die. It is the thread that links the smallest and the largest, the microscopic and the cosmic, the fleeting and the eternal. The philosophical shock of tunneling becomes even deeper in this light. If the vacuum itself is unstable, if universes can tunnel into existence, then reality is not a fixed structure, but a living process. Existence itself may be only one of many possibilities, realized by the whisper of probability. The impossible is not only real, it is the very foundation of everything. And so, tunneling carries us from the emptiness of space to the possibility of multiverses. It shows us that barriers are illusions, that nothingness is never empty, that even the vacuum hums with potential. To follow this story further, we must look outward to the cosmos itself, where tunneling shapes inflation, births new universes, and holds the terrifying possibility of vacuum decay. This is tunneling on the grandest scale, tunneling that connects the fate of stars to the fate of all existence. In the earliest moments of the universe, the rules of reality were not yet fixed. Space was expanding at a furious pace, driven by an energy locked in the vacuum itself. This period, known as inflation, smoothed the cosmos, stretching tiny fluctuations into the seeds of galaxies. But inflation could not last forever. At some point, the vacuum had to change, releasing its energy and allowing the universe to cool, condense, and form matter. The transition may have happened through tunneling. Just as a particle seeps through a barrier it cannot classically overcome, the universe itself may have tunneled from one vacuum state to another, ending inflation and beginning the cosmos we know. This idea reshapes how we think of creation. In classical physics, the beginning of the universe would demand an immense force to cross the barriers between nothingness and existence. But in quantum physics, barriers are porous. The early vacuum may have been unstable, perched in a high-energy state. Tunneling allowed it to slip into a lower state, releasing energy in a flood of particles and radiation. In this way, tunneling may not only explain processes within the universe, but the very birth of the universe itself. And if this happened once, why not many times? The mathematics of inflation suggests that it may not end everywhere at once. Instead, some regions may tunnel out of inflation, creating expanding bubbles of space filled with matter and light, while other regions remain inflating. The result is a multiverse, a vast cosmic foam, where each bubble is a universe with its own laws of physics. Our cosmos would be just one bubble, born from tunneling in the restless vacuum, surrounded by others beyond our reach. The concept is staggering. If true, tunneling does not merely shape the details of atoms or stars, it shapes the entire architecture of reality. Every universe in the multiverse may be born from tunneling, each one different, each one possible. Some may have physics where stars cannot form, others where life is impossible, and some, like ours, where complexity flourishes. Tunneling becomes the ultimate creative act, the brushstroke by which the multiverse paints countless worlds. Yet tunneling also carries a darker possibility. If our vacuum is not the lowest state of reality, then it could, in principle, tunnel again. A deeper vacuum could exist, one with different laws, and the transition to it would sweep across the universe at nearly the speed of light. Within its path, atoms would dissolve, forces would change, and existence, as we know it, would end in an instant. This is vacuum decay, a cosmic tunneling event that would erase our universe as cleanly as a wave erases patterns in the sand. The chance of such an event is unimaginably small within the lifetime of the universe, but its very possibility is a reminder that reality is not fixed. The laws of physics themselves may be contingent, the outcome of tunneling in the vacuum. What we call fundamental may be temporary, what we call eternal may be fragile. Existence itself is balanced on probability. To live in such a universe is to live in a cosmos where the impossible is always whispering at the edges of the real. Tunneling is the link between the quantum and the cosmic, between the dance of particles and the birth of universes. It shows us that reality is not rigid but porous, not absolute but contingent, not fixed but alive with possibility. And this possibility connects everything, from the improbable fusion of protons in the sun, to the decay of atoms in Earth's crust, to the fluctuations of the vacuum, to the birth of entire universes. Tunneling is the thread. It is the principle that shows us the improbable is not rare but fundamental. It is the reminder that even on the largest scales, barriers are illusions, and the impossible may simply be waiting for its chance. As we near the end of this journey, we can see tunneling not as an isolated curiosity, but as a universal truth. It is the key that links the smallest particles to the grandest cosmos. And in the final chapter, we will gather these threads together, reflecting on what it means to live in a tunneling universe, where chance rules, barriers yield, and reality itself is never as solid as it seems. In the picture painted by modern cosmology, tunneling is not just a feature of particles and nuclei, but of space itself. Imagine the infant universe, still dominated by inflation, an expansion so rapid that every fraction of a second doubled its size. Inflation was driven by a high-energy vacuum, a false vacuum, perched on a plateau of possibility. Classically, the universe should have remained trapped there forever, unable to shed the energy that fueled its furious growth. But tunneling opened a door. Just as a particle leaks through a barrier, the universe slipped through its false vacuum, releasing its energy in a burst of radiation and matter. This tunneling ended inflation in our region of space and created the conditions for stars, galaxies, and life. The mathematics of this process suggests something extraordinary. Inflation may not end everywhere at once. In some regions, the vacuum tunnels and inflation stops, creating expanding bubbles of universe like ours. In other regions, inflation continues, stretching space ever larger. The result is eternal inflation, a multiverse forever foaming with new bubbles, each born by tunneling. Within each bubble, physics may differ, because the vacuum they tunneled into may be different. Some universes may expand and collapse too quickly for stars to form. Others may lack the chemistry for life. A few, like ours, strike a delicate balance where complexity can grow. If this picture is correct, then tunneling is not only the reason our universe exists, but the reason there may be countless others. Every bubble in the multiverse is a monument to probability, a cosmos created because tunneling allowed it. To imagine this is to imagine reality itself as infinite possibility, branching endlessly, each branch a universe born from the same quantum rule that lets a particle escape a nucleus. And yet, the same process that creates universes may also end them. If our vacuum is not the true ground state, then it could tunnel again, collapsing into a lower energy configuration. This vacuum decay would not be gentle. It would rewrite the laws of physics as it spread, altering the masses of particles, the strength of forces, the fabric of chemistry itself. Atoms would dissolve, stars would unravel, galaxies would vanish. The transition would sweep outward at nearly the speed of light, impossible to outrun, impossible to predict. One instant the universe would be as it is, the next it would be gone. Though terrifying, this possibility remains only a whisper of probability. Calculations suggest that if vacuum decay is possible, its timescale is vastly longer than the current age of the cosmos, longer than the lifetimes of stars or galaxies. To us, it is irrelevant, as remote as the death of all black holes in the far future. But its very possibility reminds us that even the most fundamental laws are contingent, resting on the porous foundation of tunneling. This duality, creation and destruction, birth and death, makes tunneling the most profound of all quantum processes. It is the mechanism that allows stars to burn, yet also the one that could end the universe. It is the principle that allows atoms to exist, yet also the principle that may undo them. It is both cradle and grave, whispering possibility in every direction. And in this light, our place in the cosmos takes on a new meaning. We are beings born in a tunneling universe, living in a bubble that tunneled into existence, warmed by a star that shines because of tunneling, standing on a planet heated by tunneling in its crust, made of atoms that themselves owe their transformations to tunneling. We are children of probability, living in a cosmos where the impossible is never truly forbidden, only unlikely. In the end, cosmic tunneling shows us that reality itself is provisional. What seems fixed and eternal is only balanced on the edge of probability. The vacuum that gave birth to our universe may not be the ultimate resting place. Just as a particle tunnels through a wall, our cosmos may one day tunnel into a deeper state, rewriting its own laws in the process. This thought is humbling, even frightening, for it reminds us that the stability of everything we know rests on chance. Yet, it also reminds us that creation itself is possible only because the universe allows what should be impossible. Inflationary cosmology paints a picture of endless expansion, punctuated by tunneling events. Each tunneling creates a bubble universe, each with its own physics, each spreading outward like a drop in a vast cosmic ocean. Some bubbles may collide, others may drift forever apart, and within each, reality unfolds according to the rules set by its vacuum. Ours is one such bubble, distinguished only by the fact that its tunneling led to conditions where matter, stars, and life could exist. In this view, tunneling is the great sculptor of existence. It carves universes from the vacuum, inflates them into being, and sets their fates with the laws they inherit. It is not a rare event, but the engine of cosmic creativity, the reason there may be not one universe, but many, perhaps an infinity of infinities, each born from the same quantum rule that allows particles to seep through walls. Yet the possibility of vacuum decay casts a shadow over this vision. Just as tunneling can create universes, it can also end them. The thought that our universe could vanish in an instant, consumed by a bubble of deeper vacuum, is unsettling, but it is also a reminder of the unity of physics. The same process that powers stars, that shapes atoms, that evaporates black holes, also governs the fate of the cosmos. The same mathematics that predicts half-lives and decay rates also speaks of the birth and death of universes. For now, we exist in a vacuum that is stable enough for galaxies to form, stars to shine, and life to think about its own existence. The timescales of vacuum decay are so vast that they make eternity seem near. But the idea itself is a window into the deeper truth of reality. Nothing is absolute, not even the vacuum of space. Everything is contingent. Everything is porous. Everything is open to possibility. As we reflect on this, tunneling emerges as the thread that connects all scales of the universe. It links the microscopic world of particles to the macroscopic world of stars and galaxies, and beyond to the multiverse itself. It is the bridge between the smallest and the largest, between the fleeting and the eternal, between the birth of matter and the fate of the cosmos. And so, as we approach the final chapter, we see tunneling not as a curiosity of physics, but as a principle of existence. It is the whisper that reminds us that nothing is impossible, that barriers are illusions, that the universe is never as solid as it seems. It is the law that makes creation possible, that allows the improbable to shape reality, that keeps the cosmos alive with possibility. The journey that began with particles slipping through barriers ends with universes tunneling into being. And in this journey, we find the deepest truth, that to live in a tunneling universe is to live in a cosmos where even the impossible has a chance. From the smallest scales to the largest, tunneling reveals itself as the hidden engine of reality. What began as a mystery of particles in laboratories has unfolded into a principle that shapes stars, powers the Earth, evaporates black holes, and may even birth and destroy entire universes. It is a phenomenon that defies classical intuition, yet binds together the cosmos with a logic deeper than certainty. To live in a tunneling universe is to live in a cosmos where the impossible is never truly forbidden, only improbable, and where barriers are never absolute, only porous. Consider how the journey began. We imagined a ball rolling toward a hill without enough energy to climb it, destined to fall back again and again. Yet in the quantum world, the ball sometimes appears on the other side without ever climbing over. This image, strange at first, becomes the foundation for understanding how particles seep through barriers, how waves of probability extend into forbidden regions, and how reality itself is sculpted by chance. From there, the story expanded. Particles are not points, but waves, spreading into barriers, leaving behind faint traces that can emerge as real outcomes. This is why protons in the heart of the sun can fuse at temperatures too low for classical physics, tunneling through their electric repulsion to power the star that gives us light and life. Without tunneling, the sun would be dark, the stars cold, and the universe lifeless. Tunneling is the reason we exist. The same principle explains the steady ticking of radioactive decay. Atoms that should remain stable forever instead transform, their nuclei releasing particles that tunnel out of confinement. This decay warms the Earth's interior, drives plate tectonics, and shields life with a magnetic field. It becomes a cosmic clock, marking the passage of time in rocks and fossils, telling us the age of the Earth and the history of life. Tunneling is not only a scientific curiosity, but a storyteller, writing the chronology of existence. In the modern age, we have learned to harness it. Scanning tunneling microscopes reveal atoms one by measuring the tunneling of electrons across tiny gaps. Tunnel diodes exploit tunneling to switch with astonishing speed, enabling technologies that shape our digital world. Quantum computers toy with tunneling as both a challenge and a resource, using its strange rules to build machines that may outstrip classical computation. Tunneling is not a distant abstraction, it is a tool we hold in our hands. And yet, the philosophical consequences run deeper still. Tunneling shatters determinism, showing that the universe is not a clock, but a tapestry of probabilities. It reveals that certainty is an illusion, that even the most stable atom holds within it the chance of change. The future is not written, but open, sculpted by probabilities that unfold moment by moment. Chance is not a flaw in our knowledge, but a feature of the cosmos. In the vacuum itself, tunneling proves that nothingness is not empty. Virtual particles flicker into existence, altering atoms, pushing on plates, evaporating black holes. Even the event horizon, once thought absolute, is porous when probability is given a voice. And beyond that lies the possibility that tunneling gave birth to our universe, and may one day end it through vacuum decay. Creation and destruction, birth and death, are written in the mathematics of tunneling. To live in such a universe is to live in a reality where the impossible is always near. It is to walk on a planet warmed by radioactive tunneling, lit by a star powered by tunneling, in a cosmos that may have tunneled into being. It is to exist not because certainty demanded it, but because probability allowed it. And so, tunneling is more than a phenomenon. It is a philosophy. It reminds us that walls are never absolute, that stability is never final, that reality is never as solid as it seems. It tells us that the universe is not a fortress but a field of possibilities, open to chance, alive with potential. In this light, tunneling becomes a metaphor for existence itself. We too face barriers that seem insurmountable. We too live in a world where certainty is rare and probability rules. And yet, as the quantum world teaches, even the impossible sometimes finds a way. Quantum tunneling is the whisper of possibility in a universe of walls. It is the reminder that the cosmos is not bound by absolutes, that chance is woven into its fabric, and that reality is open, porous, alive. To understand tunneling is to understand that the universe itself is a story of barriers overcome, of probabilities realized, of impossibilities made real. And in that understanding lies the final revelation, that we live not in a solid, fixed world, but in a tunneling universe, where even the impossible is only waiting for its chance.